chapter 8 is basically integration, fancy techniques of integration. We'll just be integrating in chapter 8. Just here's an integral, compute it. There's nothing else going on in there. Now, section 8.1, you're on your own on that section. Yeah, it's basically, it's Calc 1 style integration. They'll show you some, it's a little fancier, but like if you like algebraically manipulate a little bit, it's going to work out. So there's like Calc 1 integrals in there. So there are like 5 examples. Look them over, you should be able to follow them. There's nothing new presented in that section. Okay? So review the examples, you should be okay. There are a few problems assigned on that. Now 8.2, that's where we're going to start. Okay, so you understand the, from Calc 1 you did the whole U substitution thing, and the purpose of that was to reverse the chain rule, right? That's when you do the U substitution. That's why you have a function and the derivative of the function attached to it, so that's the chain rule. You're trying to go backwards. Now, in section 8.2 that we call integration by parts, we will try to reverse the product rule, okay, in a kind of a sneaky way. So, if we look at the product rule, so if I have a product of 2 functions, and I want to take the derivative of that, the product rule suggests you take the derivative of one times the other and then the opposite, right? So let's say I can do it this way. The derivative of f times g plus f times the derivative of g. Okay? Now, if I integrate both sides the way it's written, if I integrate both sides, well, then the integral of the left is just going to be a product of 2 functions, right? So the integral on the left is going to be f of x times the g of x, while on the right, I can express the right side as the integral of g of x times f prime of x dx. And here we have f of x times g prime of x dx. And now I'm just going to algebraically solve for this integral. So if I do that, I'll get the integral of f of x times g prime of x dx equals the product of 2 functions, f of x times g of x, minus the integral of g of x f prime of x dx. So basically what this says, if you faced with an integral that has a product of 2 functions, and if you can actually think of one of those functions as derivative of some other functions, there is a way to perform that integral. It's kind of messy right now, But the thing is that f and g are totally not related. Okay, you can have a polynomial function and a trigonometric function. You can have a trigonometric function and logarithmic function. You know, they just completely have nothing in common. Like in your u substitution, that function that's attached, it's always, I mean, there is a connection in between, right? What I mean by that, don't write this down, but, you know, in calc, you know, 1, you were faced with something like that, you can clearly see how, well, there's a connection there, right? So there is also some kind of a compositional function that's going on, okay? Here you don't have any compositions. You're going to have nice, pretty functions of a single variable, but they just don't relate at all. So for example, if instead of having an x cubed on the inside, it was just an x like that. So the u substitution doesn't quite work, but this is what I'm talking about. You have a product of two functions that don't have anything in common, but there's still going to be a way to integrate that. Okay? The only problem is you have to decide which function is which. And this is going to be the half of your success. If you identify which function you want to play as f and which function you want to play as g prime. Okay? Now I'm going to change the notation a little bit just to get closer to the book, because this is a little messy. I'm just going to say call f function u and call g function v. So using that notation, the first integral is u, and this g prime of x dx is what? Is v dv. Well, not v dv, just dv. Right? The differential. You know, if v equals g of x, then dv equals g prime of x dx. Right? So u dv equals the product of uv minus the integral of v du. Okay? This is just a way to relabel things. Now let me show you this on this example. Let me just try a very simple example. X times sine x dx. Okay? So if I think about the plan here, it's really important for me to identify which function is u and which part is dv in this. Because the second I identify that, then I'll be able to fill in the rest. Okay? One thing you need to think about this, if I figure out what dv is, I'll need to know what v is and how you do that. Well, you have to integrate whatever you think dv is. Okay? So first of all, when you pick your u's and dv's, you want the dv to be easy to integrate. Okay? So the functions that are easy to integrate should be the candidates for dv. Also, think about this integral. This integral contains du, derivative of whatever you think u is going to be. Okay? So you want the derivative to be simple as well. You don't want this integral to be more complex than the original integral. What I mean by that, if I choose dv to be my x, then what is v? X squared over 2, right? And if I decide u to be sine, then du is easy, just cosine. So if I do that, I'll get x squared over 2 times cosine. Is that a better for me? That's a more complex integral than I started with, right? But if I do the opposite, if I let x to be my u, then what is du? Oh, 1, right? So then so this is nice, right? Do you agree with that? So let's try that. And I'll give you a nice little way to pick your u's and dv's. Because, well, the problem is picking your u. So in this case, if I let u to be x, then du is simply dx, right? It's 1 times dx. Is that okay? But at the same time, the rest is dv. So then dv equals sine x dx. So what is v? You integrate that, negative cosine x. And forget about this plus c thing. You just, at the end, you're just going to slap 1 plus c, and you'll be happy with that. Okay? So if I do that, then I follow this rule. The rule tells me multiply u and v. So u is x, v is negative cosine x, so I get negative x times cosine x. Right? That's the uv part. And then minus the integral of v, so that's another negative cosine x, times du. Du is simply dx. So the two negatives give me positive, so negative x cosine x plus the integral of cosine x dx. That integral you can compute, right? What is the value of that last integral? Sine x. So the whole thing is negative x cosine x plus sine x, and then slap a constant there at the end. Done. Wasn't that fun? How can we check whether that's the right answer? Yeah, if I take the derivative of all that, I should get x sine x back, right? You don't have to do it every time, but just to prove a point, if I take the derivative of this, what do we get? So the product rule over here, right? So you get negative 1 times cosine x minus x times the derivative of cosine, which is negative sine x, right? And then plus the derivative of sine, which is cosine, right? So cosine x, negative cosine x cancel, minus minus give you a plus, you get x sine x, as we started. Okay? That's how we work this problem. This is one of the better examples, by the way, where you have a polynomial and a trigonometric functions, completely different animals, but anyways. Any questions so far? Because I'm about to talk a little more about this very example before I give you all the shortcuts. Yes? I don't know. Flip the coin. We like the using these. Because it's very easy to remember, right? How do you remember this right side? Ultraviolet super voodoo. That's how you remember that, right? Ultraviolet super voodoo. That's how you remember your integration by parts. Ultraviolet super voodoo. That's why. Let's just stick to that. So, but again, this is what I'm trying to get here. First of all, dv should be easy to integrate. If your dv is a function that's hard to integrate, then that's a poor choice. At the same time, u should be a function that kind of becomes simpler when you differentiate it, right? Because if you pick your u, you need to pick du, which is the derivative. You don't want that to get bigger. So if we went the opposite, picking sine as your u, you take the derivatives of sine, it's sine, cosine, cosine, sine, who cares? But if you pick dv to be your x, it will keep growing. you'll get x squared over 2 and then x cubed over 6 as you keep integrating it. So this integral right here will get more complex than what you started with, right? Instead of, you started with x sine x, and this will be like x squared cosine x. So that's even worse. See what I mean? So the choosing your u and dv, basically choosing your u, that's the big thing, because the rest is dv then, okay? And if you choose your u incorrectly, you kind of know right away that you're moving in a direction that makes it even messier, okay? All right, well, let me try another example. What if I just do x times natural log of x dx? Okay? So I have two functions. One is x, very nice function. The one is natural log of x, right? If I pick u to be my x, then dv is the natural log of x, right? So therefore, v would be the integral of natural log of x. Do you know the antiderivative of natural log of x? No. You actually have to integrate it by parts to get the antiderivative of natural log of x. So natural log of x would be a very poor option for dv because it's hard to integrate. But it's easy to differentiate. Do you agree with that? Derivative of natural log is very simple. It's 1 over x, right? So let's try it that way. Let's try to do, let u equal natural log of x, and let dv equal whatever's left, x dx. Because x is still easy to integrate. It'll get bigger, but it's much better than integrating natural log of x. So if I label my things this way, then du is simply the derivative, so it's 1 over x dx, right? While here, if dv is x dx, then v is just x squared over 2, right? So then I need to write ultraviolet super voodoo thing. So the ultraviolet is uv, so that's x squared over 2 ln of x, right? Minus the integral of v, which is x squared over 2 times du, which is 1 over x dx. Is that okay? So many good things happen. One of the x's cancel. I can pull 1/2 out. This becomes x squared over 2 natural log of x minus 1/2 the integral of what's left. Just x. Well, that's the integral I can deal with, right? We can complete this problem by doing that last integral, which is, so it's x squared over 2, so that becomes x squared over 4 plus some constant. Yeah. So that's it. Again, if we take the derivative, we'll get the original function. I don't feel like doing it now. Okay, so what you need to understand, that the most important part in this process, well, first of all, you need to know the formula, and that's the ultraviolet super voodoo thingy. Okay, but what's really important is to pick your u properly. Okay, that will be half of the battle. If you know which function is u, the rest is dv, and then you go from there. Okay, and there is a way to shorten your struggles. I mean, you can reason through that. Again, you want your dv to be easy to integrate. You know, that's one of the options. But picking, how do you spell picking? Is that the other way? Oh yeah, picking u. So there's the abbreviation that you should know. Lipit, whatever that means. Is that a word? No? Okay, it's a word now. It helps you to pick your u. And this is basically the hierarchy of choosing u. L stands for logs. If you see a logarithmic function, that's your u. Because that's the worst thing to have for dv. Because integrating logs is awfully painful. Okay? So the logs are the first options for your u. If you have a list of functions which contains the logarithm, log is your u. I stands for inverse trig functions. Because again, those kind of hard to integrate, right? If you have an inverse sine as a part of your expression, integrating that is going to be hard. So differentiate that. P stands for polynomials. And ET, that's exponential and trig. The reason why I would say that, it doesn't matter which one you choose first. If you have an exponential times a trigonometric, doesn't matter which one is u, which one is du, because they will just circle, right? You integrate an exponential function as many times as you want, you back at something exponential, right? You differentiate an exponential function, it's just going to be an exponential function. Same thing with trig. Sine, cosine, sine, you're always going to be in this trigonometric loop, right? So those ones, doesn't matter. So exponential and logarithmic. And by logarithmic, of course, I mean trigonometric. Okay? So let's see. I might have a few examples. X e to the 2x dx. X is the polynomial function, e to the 2x is the exponential function. So according to Lippitt rule, what is my u? X. U is the polynomial. So u equals x, so then dv is e to the 2x dx. Okay? So then if u is x, then du is just dx. What is v? 1/2 e to the 2x. You kind of have to do a quick u substitution to come up with 1/2, but I'm sure you should be able to realize you need 1/2 because of the 2x, because of the chain rule. All right. Is that okay? Then throw it all into the formula. uv, so uv gives you 1/2 x e to the 2x minus v du, which is 1/2 e to the 2x dx. Right? So you have to integrate e to the 2x again, which is again 1/2 e to the 2x. So you'll end up with 1/2 x e to the 2x minus 1/4 e to the 2x plus a constant. And we're done. Any questions on this? Actually, it's not as bad as it seemed originally. If you know how to grab that u right away, then you just follow the formulas for the rest of this process. And it should be pretty straightforward. Well, most of the time. So let's start having fun with this stuff. Are you ready? We're just going to integrate for the rest of today, or the rest of the next few weeks, we'll just be integrating. What? You think this is good? Oh. I mean, I know we're not rotating anything or whatever, but here's a juicy one. Do I really want to do that one? Oh my God. Okay. Yeah, this is a juicy one. You're going to love it. X squared times sine of ax dx. Now, this one is actually just like a 2-pager. going to be. These are my notes on this question. And I tend to skip steps. But the easy part, what is u? X squared, the polynomial before trigonometric. So u equals x squared, then dv is whatever's left. Yeah, we're going to have to do this several times. So then du equals 2x dx. And then v is what? So 1 over a negative 1 over a cosine of ax, right? You need 1 over a to kill the a as a part of the chain rule, right? Is that okay? All right, so uv, so it's negative x squared over a cosine of ax minus the integral of v du. So negative negative makes it positive, right? V is negative. 2, 1 over a, I can pull them out. And we're left with x cosine of ax dx. So are you okay with the two negatives, positive, 2 over a is a constant? Pull that out. We'll have to do it again because it's, again, a product of polynomial and trigonometric. But the good news, this product is a little simpler than that product, right? As you notice, the quadratic became linear. So if I do it one more time, the linear will become a constant. It will be gone, so I'll be stuck with probably a sign of sorts, right? So I just need to do it one more. If this was a 4th degree, if this was x to the 4th, sine ax, then this would be x cubed. You'll do it again. X cubed will turn into x squared. You do it again. X squared will turn into x. You do it again. And then you're done after one more integration. So there'll be like 6 terms in this or whatever. But anyway, so I need to integrate by parts that one, right? I'm going to take this problem separately. So I'm just going to take x cosine of ax dx. And it's totally okay to label things u and dv again. I know we already used those letters in above, right? But we're already done with u dv over there. It's all converted into x dx. So, you know what I mean? Don't put like s and whatever dt's in there. Just stick u dv. Will be easier. So what is u here? X, so du is dx. So what is dv? So whatever's left, so it's cosine ax dx. So v is 1 over a sine of ax. Right? So this becomes uv x over a sine of ax minus v du. 1 over a is a constant. So that's just the integral of sine of ax dx. Right? That integral we can do. What is the integral of sine of ax? That's right. We already did it. It's right here, right? So the whole thing becomes x over a sine of ax. Since the value of this integral comes out negative, negative and a negative give me a positive. 1 over a give me 1 over a squared cosine ax. Right? You can put plus a constant if you want to. So this part takes the part of that in our previous integral. Right? Because we did that one on the side. Are you following that part? So then our answer, the integral of x squared sine of ax dx equals negative x squared over a cosine ax plus 2 over 8 times all this, right, the thing in the box, x over a sine of ax plus 1 over a cosine of ax, and just again, just plus c somewhere. I don't want to mess with the c times 2 over a, some other c, I don't care, just plus a constant. I mean, that's technically your answer. Yeah. Yeah, that's 1 over a squared. I mean, you can distribute there. I'm sure there's, there you can factor the cosine partially, whatever. That's the answer. It's that big messy thing. So how is that? It's not bad, right? I mean, I don't know. Let's try this one. From 1 to 4, let's do a definite integral. Square root of t times ln of t dt. So two not related functions, square root of t and natural log of t. What's our u? Ln of t, right? I mean, by the way, we think of square root of t as a polynomial function. P can be interpreted as a power function. So t to the 1/2, that's in the polynomial family, just in case. But yes, u is ln of t. Then dv will be, let me write it as t to the 1/2 dt, because we're going to integrate it separately. So du is 1 over t dt. And v, you just have to integrate t to the 1/2. So it becomes t to the 3/2 times 2/3 by the power rule. Is that okay? So uv, so 2/3 t to the 3/2 times natural log of t. Remember, that's a definite integral, so that thing is still evaluated from 1 to 4. We have to do that. I mean, we can do them separately. Minus the integral of what? V du? Yeah. Well, because it's everything in terms of t, right? So limits will stay the same. So that's 2/3 t to the 3/2 times 1 over t dt. But yeah, since we're keeping everything in terms of the original variable, the limits will stay the same. So what happens here, we can reduce the integrand. T with 3/2 gives us 1/2 back, right? So we're integrating t to the 1/2 again. But it is weird to keep track of all the computations. So 2/3 times, so this is 4 to the 3/2 times ln of 4 minus, well, that's going to be 0 when you plug in 1. So as that first thing evaluated, minus So it's 2/3 times integrating t to the 1/2. We already did that, so it's another 2/3 times t to the 3/2 evaluated from 1 to 4. Right? So whatever that thing numerically. So it's 2/3. 4 to the 3/2 is 8 times natural log of 4, whatever that is, minus, that's a 4/9. So you have, plug in 4, you get 8 minus 1. Whatever that is, numerically. Did I compute that? Yeah, I didn't even bother computing that. So 16/3 ln of 4 minus, what is this? 7 times 4, 28, 28/9. So whatever that is numerically, that's the value of the integral. Somebody's punching that in. What'd you get? All right, 4.28. So over here, right, plug in 4 first. So it's 4 to the 3/2 times ln of 4. But then when you plug in 1, ln of 1 is 0. So, well, sure, I mean, it's still, it's part of the antiderivative. I mean, I can find the antiderivative and then evaluate it. It's up, that doesn't matter. So I can split it into 2. So yeah, I'm still evaluating the antiderivative. Is that okay? Well, because uv, it's already part of the antiderivative. There's no dx's or anything like that, no dt. So it's already, we're done integrating, so go ahead and plug it in. Now still integrate the other part. I mean, I can do the full antiderivative first and then plug in values. That doesn't matter. You can ignore the limits, find the antiderivative, and then do the limits. You should still arrive at the same answer. Good stuff? Questions? Okay. Well, let's try this one. We did this problem on the very first day of the semester. The solution to this problem was the reason why you want ln of x to be your dv. Because if ln of x equals dv, you actually have to do this problem to integrate ln of x, and to do that problem, you have to do it by parts. So from everything that I said already, what our u should be? ln of x, lipid, right? L is for logarithm, so u equals ln of x. So what is dv then? What? dx. What's left? dx. So dv is dx. So then du is 1 over x dx, while v, well, v is just x. Okay? So then we go through the process. uv is x ln of x minus the integral of v du. So that's x times 1 over x dx. Is the setup okay? So x's cancel. You just have the integral of dx. So this is x ln of x minus the integral of dx, which is just x. So x ln of x minus x plus a constant. So that's the antiderivative of natural log of x. It's a little messy. Questions? Ready for a fun one? Let's do a fun one. I don't know. E to the x sine of x. Two functions are completely unrelated to each other. One is exponential, one is trigonometric. What's our u should be? Either one, right? It's Lipit, ET, whatever. So let's e to the x as good as anything else. So let u equal e to the x. So then dv equals sine x dx, whatever's left. So then du is e to the x dx, and v is negative cosine x, negative cosine x. What? Negative cosine x, right? So if I put everything together, uv, so it's negative e to the x cosine x minus v du. Well, we have another negative. Do you mind if I just put a plus in there? And then it's e to the x cosine x dx. That's what it seems to be. Because this is the two functions, none of them will ever go away. You're always going to be stuck with a similar integral. Right? Do you recognize that? And if I keep going, but for now, the only option that I have that integral, e to the x cosine x. Well, if I try that integral separately, and I do it the same way, u is e to the x, and dv is cosine x dx, then du is e to the x dx, and v is sine x. Right? Integrating cosine, you get your sine. So if I put it all together here, uv e to the x sine x minus v du e to the x sine x dx. Yes? What? Were you trying to relate your question to this problem? Oh, well, I mean, whatever it is you're saying, yeah, we'll try that too. But this one, we don't need it here. We're actually almost done. Believe it or not. We're actually closer to the answer than you think. Because what is the original problem? Let's copy it over. So it's so it's the integral of e to the x sine x dx equals. So we have negative e to the x cosine x plus this integral, right? Which is e to the x sine x minus e to the x sine x dx. This is where we're at? What? I can just add that in over both sides because I'm solving for this. This is the unknown, right? This is the unknown. And it also appears there. This equation to me right now is x equals blah minus x. How can you solve for x? Yeah, you add x to both sides. Add x, add x. So this is 2x equals blah. And by the way we spell blah, there's no x's in blah, right? So I can just do that. So divide by 2, x equals blah over 2, right? So I can do the same thing here. If I add that integral to both sides, it cancels over there, gives me 2 integrals of e to the x sine of x dx equals that. Let me write it pretty. E to the x times sine x over minus cosine x. Right? I can factor e to the x out. Well, can we solve for that integral? Divide by 2. So the actual value of this integral is all that so sometimes when you get into those loops, the thing starts repeating itself, so you can actually solve for it algebraically. Because this step right here, that's a linear equation. Right? You have your unknown on one side and unknown on the other side. Get them all to the same side and then solve. Did that make sense? Because again, this is the same integral. It appears on both sides, so we can start using algebra from there on. So usually that's what happened with those trig times exponential functions when both of them. I mean, and it didn't matter. We used u as e to the x. If we started u to be sine x and dv to be e to the x, it will still get to that point. How's that? All right. Well, I'm going to give you a problem. Try this one. It's very similar to what we just did. E to the negative theta cosine of 2 theta d theta. Try that one. I'll get a drink of water. But again, it doesn't matter what's u, what's du here. How did you guys want to set this one up? What do you want u to be? All right, let's use e to the negative theta. Then dv is cosine of 2 theta d theta. So then du is negative e to the negative theta d theta. Is that okay? And then what is v? One half sine 2 theta. Okay. So if we put everything together, we'll get negative e to the negative theta over 2 sine of 2 theta, right? Minus v du, one of those is negative, so it becomes plus the integral of e to the negative theta, can kick 1/2 out, and then sine of 2 theta d theta. Is that okay? Do it again, right? So I'm going to take this integral on the side, e to the negative theta, sine of 2 theta d theta, and I'm going to let u equal e to the negative theta, and dv equals sine of 2 theta d theta. So du is negative e to the negative theta, right? And v is negative 1/2 cosine 2 theta, right? So let me just put it all back here. So equals negative e to the negative theta over 2 sine of 2 theta plus 1/2. So uv, so that's negative e to the negative theta over 2 cosine 2 theta right? Minus the integral. These two are negatives, so still going to be negative. So 1/2 e to the negative theta cosine 2 theta d theta, right? Yeah. Uh, no, so that's uv, right? Yeah, they're both cosines. Is that right? But the point is that this is the same integral as on the left. So we just need to figure out the coefficients. So this is negative e to the negative theta over 2 sine theta minus e to the negative theta over 4 cosine theta, right? And then minus 1/4, is that right? 2/3? Oh, yeah, 2 theta, yeah, that's, thank you. 1/4 e to the negative theta cosine theta d theta, still in the integral. Yes. Is that okay? So we're going to add this integral to that side. So that's 1 plus 1/4. So that's 5/4. So we'll get 5/4 times our integral. I'm just going to write big I there, because for the sake of not messing up the 2 theta part. Equals, can I do some factoring? The 1/4 are going to play. I'm going to pull what? Is this right? Yeah, so let's pull negative 1/4 e to the negative theta out. That leaves us with 2 sine of 2 theta plus cosine of 2 theta, right? And so multiply by 4/5 to get rid of this. So our integral is negative e to the negative theta, 2 sine 2 theta plus cosine 2 theta all over 5. Because I think that's what I got before. No, I'm missing a sign. Maybe I did it wrong before. Are the signs okay? I had a wrong sign before. No? Like a plus minus. Like I didn't get both negatives. One of them was positive, one of them was negative. We're there. Yeah, but v is negative. Oh, you're right. So this should be a plus. Yeah. Good. So then it changes a plus here, a plus here. So then a plus here and a minus there. That's what I got before. Yes, thank you. Plus a C. So that, yeah, Greg is right, because this is UV, so they're both positive. So plus. But anyways, that's how you do these, the ones that loop around. You have to solve for them algebraically. Is that okay? I have with, okay, well, this is the last one that I have for you, and this is going to be fun. So this is sine of the square root of x, okay? So this looks like a composition of two functions. And when we do integration of compositions of functions, we kind of use this U substitution, the Calc 1 style, right? Whatever it is we're doing right now, our integrals, when you do integration by part, you don't want to have this kind of composition where it's composition of literally two fancy functions. I mean, we can handle things with simple composition when it's just the constant multiples. This is okay. But this one gets a little messy for our purposes. So, but if we start with just U substitution, like a Calc 1 style substitution, what do you think our U should be? The square root of x. Usually go for the inside function, right? Now, for the sake of not messing with lots of u's, I'm going to make a t substitution in this one. I'm going to let's say let t equal the square root of x, just like you do let u equal the square root of x in Calc 1, because I'm going to use u for my integration by parts, hopefully. Okay, but if I let this happen, what is dt then? Yeah, so 1 over 2 square roots of x dx. So then dx is 2 yeah, 2 root x times dt. Okay, so if I make that substitution, I'll get sine of t times, instead of dx, I have 2 square roots of x dt. Yeah? That's exactly what I'm going to say, because again, I want to have the same variable. Square root of x is t. So this becomes an integral of 2t times sine of t dt. Right? It no longer has the composition. It's just sine of t, simple function. Got an extra t on the outside. This integral can be handled with integration by parts now. Because I have a polynomial function times a trigonometric function. So if I actually do this one by parts, I'm going to say let u equal, well, let's just make it 2t for this, then, well, let's make it t. Doesn't matter. But you see what I'm trying to do here? I'll do this one by parts. Let's make it t. So then du is dt, and v is negative cosine t, right? So the whole thing, I can pull the 2 out. So it's uv, so it's negative t cosine t minus the integral of v du. So v is negative, so that makes it a positive. And this is just cosine t dt. Right? That integral we can do the cosine t. What is the integral of cosine t? Yeah. And then I can substitute back. Because what is t equals to? Yeah, square root of x. So the whole thing becomes 2 times negative square root of x cosine of square root of x plus sine of square root of x plus a constant. So we kind of had to do the Calc 1 substitution to make this integral, well, more friendly in terms of integration by parts. So, and the more friendly makes it that it doesn't have a complex composition like it had originally. Still worked out. Questions on this one? Well, let's try. Yeah, that might have not worked. I mean, if we try this one, sine t squared, I'm sorry, x squared, right? Doesn't matter, but x squared dx, like that. So if we try the same pattern, t equals, I think it will work. T equals what? X squared. So dt equals 2x dx, right? Yeah, it'll get ugly, I think. Well, so dx is dt over 2x, right? So if we make the substitution, this becomes sine of t dt over 2x. So what is x? I mean, technically it's square root of t. I'm not sure how to handle the plus or minus part yet. But if we do it that way, so what does it become? 1/2 comes out. So this is t to the negative 1/2 sine of t dt, right? So if we try to do the integration by parts now, I don't think it'll give us anything good. Because that, even if we try this is u, so du is negative 1/2 t to the negative 3/2, right? And this is sine, so some version of cosine. So our new integral is messier, right? If we do it the other way, I mean, if I let u to be my sine and t to the negative 1/2 to be dv, you'll get the square root, right? I don't know, I don't think it'll work. If we do it this way, so, right? Um, Let me try something. So is that, that's what I'm thinking about, but yeah, but the thing is, if they have the same coefficient, then it just doesn't work. They'll cancel each other. If we get a different coefficient, because this is going to be uv minus the integral of v, so that's 2 t to the 1/2 du cosine t dt, right? So if I let u to be t to the 1/2, so then du is 1/2 t to the negative 1/2, and dv is cosine t dt, and v is sine t. So what is that going to be? This is negative. So whatever the uv is, minus 2 v du times 1/2 t to the negative 1/2 sine of t dt, right? So we get coefficient of negative 1. So you add it, you get 3/2, right? Let's see. So we're getting 3/2 times our integral equals, what was v in there? 2t to the 1/2 times sine t. Is that right? So the integral is 4/3 t to the 1/2 sine of t. Yeah, I had another UVs. So what is the other UV? I should have been more careful. So the other UV was, so I also have a minus. Oh, they'll just cancel. They'll just 0. right. So yeah, that does, because yeah, when we flipped it, you get 2 of those, but then minus 2 of those, right? Those are the same, so they'll just be 0. So that didn't work. Some of those are sad. All right, good. So you have a homework on 8.1 and 8.2 posted. So 8.1, just review some of those examples. They're Calc 1-ish with some tricketry to them, but it's a simple tricketry. Just kind of look over. And then you have that for Wednesday.